Okay, good morning. Welcome to
FamilyMath number 878.
FamilyMath878. So I saw a really cool program shared online by Craig Kaplan, and had you guys play with it this morning. So there were what
93.
There were 93 different tiling patterns called isohedral tiling patterns, and said you play and pick 3 that you found interesting. So go ahead, tell me what you found.
So this first one's number 31. And we have these kind of hexagonal wedges that are tiling. You can kind of see the hexagons. And then this is cool because you can kind of alter the shape by adding vertices.
Wait, when you say hexagonal wedges?
So, like, they don't make up a hexagon, but if you can see that you have 6 of them here.
Oh, I see what you mean.
And each of these is half a side length of a hexagon.
I gotcha. Okay, cool. Yeah, nice. Sorry, I was looking at that wedge and I only saw 4 sides. Now I see what you're talking about. All right.
So you can kind of add vertices and kind of like distort the pattern a bit. You can see how it's changing. This is cool because it gives you, like, maybe you wouldn't think this shape tiled, but here's the tiling pattern for it. And then, I don't know, I think, yeah, there you go. You can, it's kind of hard to tell which ones you can add on. Well, you can make some, hold on, I'm just adding vertices. You can make some kind of really weird shapes, even shapes that really don't make sense, like this shape.
Why does that shape not make sense?
Well, just like, this is just a really weird shape that just at first glance you wouldn't think this shape tiles.
Interesting.
But here's a tiling pattern for it.
Cool. All right. What was the next one you thought was interesting?
Next one was number 36, I believe. It skips 35 for some reason. But
all right.
this is kind of cool because you have a rhombus tiling pattern that looks like stacked cubes going up.
Yeah.
And then I kind of like this one for the same reason, because when you go like this, you can kind of distort the cubes. Actually, you can make it into hexagons if you want to.
Huh. That's a surprise.
And then kind of just like goes up and down like that. And then I guess they have to have these extra points. They move in some sort of pattern to each other, so that it keeps them being able to tile.
Yeah.
But again, like at first glance, you wouldn't think this shape tiles, but here you go.
So when you clicked on that point to add a point or move it around,
it added 4.
It added 4. So what do you think's going on there?
Well, it probably needs to do that. I mean, you need to be symmetric, and it also probably needs to preserve, I guess, how it tiles, because they're not making new ways to tile. They're tiling in the same way that they originally tile. But I guess that's how they would do it. And when you move the top 2 in, the bottom 2 move out, and vice versa.
All right, cool. Let's take a look at the last one.
All right, that's a little far. It's 78. So
We'll get there.
So here's a right triangle tiling pattern. I don't remember if it was actually this one or it might have been the next one, but you can still kind of see how you can move it around into like even shapes, like this weird double triangle shape still tiles.
Yeah.
You're not really adding a point here, you're kind of adding this line that moves around. I think it's kind of a better way to think about it than adding 2 points, because they're strongly related here.
That's interesting.
Some of the vertices I can add more. It's like this shape. You wouldn't think this shape tiles, but it does tile.
What does the slider bar do on this one?
I think it's the width of this shape, like here. I think it's the height here. You can kind of slider bars are kind of weird. You have to click where you want to go. But it makes the shape taller and shorter. It changes. It's this vertice and this vertice. It changes the distance.
So, let me ask you, what do you think is the math involved in creating this kind of computer program, or math involved in studying these kind of tilings? What do you think Craig Kaplan was doing behind the scenes here?
Well, they're all pretty simple tiling patterns to begin with. You're not doing anything complicated with like the pentagon tilings. Although it'd be cool if they had the pentagon tilings. But you're doing like squares, hexagons, triangles, rhombi. So it's pretty simple tiling, and then you can, I guess, there's each individual, actually I can zoom in. There's like an individual square or an individual unit that you can kind of figure out how the distortion would go so that it doesn't impact the overall look of the unit, and then you can just copy that along.
Yeah, that's some interesting math ideas. Any other math ideas you think are happening here?
Well, it's probably a lot of similarity and congruence ideas from geometry. Mostly, maybe you can kind of split this shape into like triangles and try to find the similarities between them.
Ooh, yeah, maybe that sounds very tricky. But you know what? This program actually itself might be very tricky. So cool. What do you think about this?
I think it's cool, but it would be cool if they had, I guess, more complex tilings, like pentagon tilings would be kind of cool to see in here, or like octagon, something with an octagon, or higher, I guess, bigger shapes.
Yeah, this is actually a special class of tiling, actually very similar to the class of pentagon tilings. This is a special class of tilings, so he wasn't trying to make all possible tilings, but he was trying to make these
specific tilings.
These isohedral tilings. And to be honest, I actually don't know what they are. When I saw his post, was the first time I'd heard of them. But I thought it was really cool to play around with. And he spent a lot of time working on this. In fact, in his post, I think he said his PhD thesis was about these, and classifying them, and studying them, and then also working out how you do the graphics. So cool. All right, good job, man.